Next speaker is Professor Karimi from the same Department of Chemical Biomolecular Engineering and NUS. And today he's going to share with us on lowering carbon emissions via energy integration and hydrogen. Professor Karimi, please.
Hello, good afternoon, everybody. Can you see my screen?
Yes.
Okay, good. All right. So I'm going to be brief. As you can see here, I want to talk about lowering carbon emissions in two ways. I'm going to, because we have two projects that we are doing under Singapore Energy Center. One is a core project, and the other is a member-specific project. So the core project is on lowering carbon emissions using energy efficiency or energy integration in chemical plants. So it is the traditional, the first way of defense against climate change and carbon reduction. The second one, which is the member specific project, is on hydrogen, which is basically our way to decarbonize our economy and remove carbon from the energy scene. This has been truly an excellent collaborative project. From NUS, we have 3 PIs involved, myself, Prof. Farooq, and Prof. Wang. A number of postdoctoral fellows have been involved in these two projects. Dr. Nicholas and Dr. Thaure were involved in the hydrogen project, and Dr. Garud and Dr. Sinha are involved in the energy integration project. Also, 2 PhD students have contributed over the years to the integration project. So these are Dr. Sajid Nair and Dr. Hamidi. And I must say that we were very happy and fortunate to have excellent participation and collaboration with Adam, Brian, and Rob from ExxonMobil. In fact, the idea of hydrogen project was conceived by them, and they have hugely contributed to the hydrogen project, and really guided us very well. Okay, so before due, let me go. So our objective, basically, if I can, I don't know, this thing doesn't go away anyway. Okay, all right. So our interest in, so I'm going to talk about hydrogen project first. Our basic interest in hydrogen project was to analyze the future of hydrogen in the ASEAN region. As we know, ASEAN is obviously growing in population rapidly. GDP is increasing, lots of developing nations, and the energy demand and power demands are increasing. And interestingly, the region provides a diversity of resources, right? You have solar energy availability, you have biomass availability, you have coal, you have natural gas, all that. So all kinds of natural resources are available, and that obviously becomes an interesting problem. We also have a diversity of trade flows. So for example, something like Singapore does not have natural resources, so probably we'll have to import energy from outside, versus let's say Malaysia or Indonesia, where they have natural gas and they have other area required for solar energy and all that, so they can produce energy. So this makes a very good supply chain for hydrogen. Okay, so our objective was to really understand how could, or how should, or how would hydrogen develop in ASEAN. And also, obviously, we had special interest for Singapore as well. So we also are looking at studies, case studies for Singapore, to try to figure out what will happen. And so our objective was to basically do a techno-economic environmental analysis, where we want to look at it from a cost perspective, obviously is very important. We also want to look at it from a technology perspective, right? I mean, what is the level of technology? What is the progress in technology? How will the technology develop and things like that? And also we want to look at the environmental aspects, which is obviously very important, right? We want to look at the CO2 emissions because we have to spend energy for developing hydrogen, and what is the impact of that energy on the overall evaluation of hydrogen and how it would evolve. So it's basically entirely a very an excellent supply chain, and we wanted to not really look at the static picture of current picture or maybe next 5 years or so, but if we wanted to see how things would evolve for up to, let's say, 2050, right? So that's our basically the objective of the study. Now, if you talk about hydrogen supply chain, right, there is this 200 years legacy of carbon, right? We cannot get rid of it overnight, right? So there has to be two other supply chains which become very important. And I know that Prof. Linga is going to talk about CO2 sequestration and all that, and so he's going to be talking about CO2 supply chain. But as you know, LNG and natural gas is going to be very important, right? We cannot get rid of our legacy in overnight, so we got to have a transition period where before we switch fully to H2. So natural gas supply chain becomes important. So this basically represents the scope of our supply chain, which our study, which involves three supply chains. It involves things like, for example, power generation with carbon capture and concentration. It also involves carbon capture and utilization, where we can use natural gas to, for example, produce hydrogen, but with carbon capture and storage. Okay, and then we can use that carbon to convert it into products which could be fuels for transport. We also, because we can use solar energy to produce hydrogen, this hydrogen can be supplied to power plants, which has a mixture of natural gas and power and hydrogen. It can also be supplied for heating needs. It can also be supplied for transport sector, and transport sector could have land, aviation, and marine. So basically, this is the overall scope that we are looking at as far as hydrogen evolution in ASEAN is concerned. And I think the crux of the story is basically the highlight of our project so far has been development of a highly interactive tool, which we have termed as HARD, basically which is a hydrogen economy assessment and resource tool, which is developed in Python, but it has several components. So the first of all, it has a database which is basically based in spreadsheets, so people can put in the data for production, the carbon emissions from production of hydrogen, the demand for hydrogen, the transport, ways of transporting hydrogen, and things like that. So that's basically your database for information. Then you have an optimization engine which basically solves a planning problem. It solves a planning problem to figure out, where should you produce hydrogen, how much hydrogen should be produced, what technology should you use, right? Where should you look at these things, etc. What transport mode should you use to transport hydrogen, things like that. So this is basically a very complex optimization problem, which can be solved using an environment optimization environment called GAMS, which is generalized algebraic modeling software, which we have been using for many years now. And so it involves solving this optimization problem to come up with a plan. And then obviously it has this graphical user interface to interface with either the user who is trying to get some scenarios tested, or also some administrators or policymaker who can provide some data. Okay, so we have input, and the basic output, as I said, would be the cost of hydrogen, delivered cost of hydrogen, the emissions which are involved in the supply chain of hydrogen, the projections of demand, transport costs, and a plan for expanding hydrogen production and transport. Okay, we allow a number of routes so far in our study. As I said, right, the study is still ongoing. But at this point in time, we have focused on using fuels like natural gas, coal, and biomass to produce hydrogen using conventional biogas gasification technologies like SMR, autothermal reforming, and POX, partial oxidation. And also we have used water splitting. So basically we can use grid electricity to produce water, or we can use obviously renewable electricity to electrolyze water. And so what we call is that if hydrogen is produced using renewables, then we call it green. If it is produced using fossil fuel with CCS, right, we have not considered the option of gray hydrogen, which is emitting carbon, because obviously our objective is to reduce carbon. We cannot afford to emit carbon while producing hydrogen. It doesn't make sense. So we have only used blue hydrogen. We are allowing a variety of transport modes to evaluate. So for example, we consider that 20 bar H2 is generated either from renewable electricity, water electrolysis, or fossil fuel, etc. And it is supplied via pipeline to the supply chain of hydrogen. So our supply chain basically begins here and goes all the way to the end consumer, who can use hydrogen in terms of a 20 bar hydrogen gas, or he can use it in terms of a liquid NH3, or he can use it in terms of 700 bar hydrogen, such as what would be used in transport sector. Okay, now between these 2 points, we allow a number of modes of transport. So we allow it pipeline transport, so and we allow trucks, and we allow ships. So this transport is going to be between the export terminal and import terminal. So in our tool, we allow to locate export terminal, we allow locations for import terminal. So if the export terminal is located on the land, then you can use a pipeline to transport hydrogen, or trucks to supply hydrogen. If it is located overseas, like for example in Australia, right, we would use a ship to transport. So all of these modes, intermodal modes of transport, are allowed in the tool. And you can also deliver, or you can also transport hydrogen in various forms. You can transport as a liquid, you can transport as a methyl cyclohexane as an organic carrier, you can convert it to ammonia and transport as a liquid, etc. And in the truck mode also we can allow several transport. And for the pipe mode, we allow liquid NH3 as well as compressed hydrogen. So as you can see here, so 2 products, one raw material, one material, one input, and various ways. And basically our objective is to find out the best way to transport these things and estimate the cost. So I'm not going to go through all the detailed results. Okay, I'm just going to give you a glimpse of a few results and summarize the results. Basically, this is the type of results we can get from our tool. Basically, it will tell you what is the relative. I mean, I emphasize the word relative here because these cost numbers depend on a lot of factor, right? And even I cannot imagine, I cannot remember all the possible inputs that have gone into generating a figure. So I normally, I want to emphasize the fact that I think what is important is not the actual number right now, right? We can always finalize this number with reliable cost data, but how the relative cost appears for various modes of transport. So here what we have done is that we have been able to identify the cost of the raw material, which is the hydrogen, and cost of the supply chain. So this part represents the cost of the supply chain, this part represents the cost of the source material. So at this point in time, as we said, we have taken $6 per kg of hydrogen right now. Transport distance of 5,000 kilometers. So this is basically a study between Australia and Singapore. And grid electricity, and again, as I said, grid electricity is not going to be totally renewable all the time. It could also involve, conventional LNG source. So we have taken the cost, which is a composite cost. So right now, if you take $200 per megawatt hour, this is the cost picture we get. We see that if you use ammonia directly and transport it by liquid ammonia, that would give you the cheapest hydrogen. While if you use liquid hydrogen to transport, you would have the costliest hydrogen. Okay, right. But I think most important thing is that the production cost, that is the cost of hydrogen, is comparable, right? Obviously, is more, but is comparable to the supply chain cost. So you cannot really neglect any aspect of this. So we need research both in producing hydrogen, as well as research in transporting or supply chain of hydrogen. Now look at this interesting, right? If I just change the grid electricity, keeping everything else same, I just reduce the electricity cost by half, you can see that now liquid hydrogen becomes comparable to, let's say, liquid ammonia, right? And then liquid MCH and liquid ammonia are not so comparable, are more expensive. So there is a huge complex interplay of lots of factors, right? Factors like transmission distance, the emissions, the production technology, the cost of raw materials, the cost of electricity, cost of fuels, etc., and the cost of transport. So I think, you just have to, as I said, be very careful when numbering. So here is just a glimpse of the result that we have got. We have already published this paper in International Journal of Hydrogen. Here you can see here is that, look at the energy penalty. Okay, what is the penalty that you pay for transporting hydrogen. As you can see here, for less than 4,000 kilometer, if you use liquid hydrogen, you pay the most penalty, right? Ammonia, methyl cyclohexane, not a big problem. They are comparable. But if you transport hydrogen via pipeline, you have the least energy penalty. All right. Okay. If you transport, for example, if you deliver 20 bar hydrogen to power sector, as you can see here, for less than 2,000 kilometers, liquid hydrogen is the most expensive, and pipeline transport is the least expensive. And similarly, if you transport 700 bar hydrogen for transport sector, liquid ammonia comes out to be and MCH comes out to be better, is the most expensive, and it's even more expensive than liquid hydrogen for less than 4,000 kilometers. But pipeline still comes out to be better. So here, as you can see here, this is the graph for pipeline. This is the violet is the curve, is the plot for using ammonia directly, whether for power generation or for transport. And so, as you can see here, in many cases, for less than for across many distances, direct use of ammonia seems to be quite promising. Okay, but all right. Okay, so I think so that basically gives you a glimpse of. So before I, so that is the summary for the first project, hydrogen. For the second project, it relates to integration of energy. I think we are all familiar with, many of us are familiar probably with energy integration in chemical plants, where basically you use hot fluids to heat cold fluids, etc. Okay, so basically it's a heat transfer, right? Is a transfer of heat. But there are many chemical processes where pressure is involved, and this is where we got the idea. Where you can actually integrate work rather than just integrating heat. So what we have been doing in this project is that we are trying to develop methodology for work and heat integration in chemical plants which are in a cluster. So for example, Jurong Island, right? Now, there is a lot of study done for intra-plant integration of energy, right? Heat basically, right? Not even power. So we have done obviously some work on the power and heat integration, work and heat integration. But what we are trying to do now is trying to see how we can exchange heat and work between plants, right? So it involves collaboration between enterprises, entities. So there are lots of problems involved as far as logistics and control and stability and responsibility and safety, etc. So we are looking at all that comprehensive picture to figure out what is the best way to transfer, exchange work as well as heat.